Yes. So here comes to our third speaker, Professor Xu Yang from Fudan University. He will be talking about AI data centers from technical characteristics to challenges and system issues. Okay, this is time.
Okay, thank you. So today I would like to share some of our recent works on AI data center networks. So as we know that in the past decade, AI models, the size has increased dramatically, and many frontier large language model has entered the training parameter region. And at the same time, the large language model inference also, the demand increased dramatically. So according to OpenRouter platform, so the major AI models received huge jump demand in the past 12 months. So with such a large AI model size and huge inference demand, so many technology companies have designed specialized AI clusters to support this computation requirement. So these companies, although use different, slightly different implementations, they share many similar design choices. For example, all this design for the AI fabrics use multi-tier, multi-plane, and real-world connectivity design. So this specialized AI fabrics provide a huge throughput and low latency connectivities among huge number of GPUs. So why do we need this specialized AI fabrics? The major reason is because today's AI workload is very different from traditional data center applications. So if we consider training as an example, there are lots of parallelism has been used. For example, data parallelism, EP expert parallelism, tensor parallelism. All these parallelism have generated different collective communications and activation transfer of data. So the mix of this parallelism has generated very complex data pattern between the GPUs. Now, if we consider inference, many major AI systems has adopted a disaggregated structure. For example, they disaggregated prefill and decoding, and even attention and FFN. So when this computing components have been disaggregated, it will trigger lots of data movements. Okay, for example, we need to transfer keep cache between prefill and decoder nodes, and also when we do AF disaggregation, we also need to transfer activate data between adjacent layers. So because of this difference, we require specialized AI fabrics optimized for AI computation. Now here we summarize 3 key features for AI networks. So the first feature is that the AI traffic demands both low latency and high throughput. So here let's use the DeepSeek V3 as an example. Suppose a decoding step use a batch of 128 tokens, and each token is represented by 7,168 vectors. So suppose we use 8 experts for the routing. So you can see for each layer, the all-to-all communication between experts will generate about 22 megabytes of data. And in this design, suppose we want to achieve a TPOT, time per output token of 20 milliseconds. So that's equivalent to 50 tokens per second. So we have only 327 microseconds for each layer of processing. So here, because we have 61 layers, so each layer has only 327 microsecond budget. Now, if we spend 50% of this budget on communication, so the communication budget is only 163 microseconds. Okay, suppose we equivalent very high-end network. Okay, so each server is equipped with 8 to 100 Gbps NIC. So the total transmission rate for a server is 1.6 T. So it's very huge rate. The ideal transmission time, okay, for this 22 megabytes is 110 megaseconds. So even in ideal network condition. So that means we only have 53 megasecond delay jitter budget. Okay, so even a small bandwidth fluctuation or queue buildup will lead to violation of the delay. Okay, so basically this example tells us that AI traffic requires both low latency and extra high bandwidth. And the second feature is that the AI training will generate the periodic and synchronized burst traffic. So because we use lots of different parallelization, and this parallelization generate different periodic traffic with different durations and the frequency. So when this parallelization are mixed, so the periodic traffic will also overlap and generate even more complex of periodic traffic. So if we design the network based on the peak traffic rate, that will cause huge network resource waste. Now, if we can predict the periodic traffic, we can predict when the traffic gonna come and what's the volume of the data transfer, then we can prepare for the network resource in advance. So that's actually bring both challenges and opportunities for our AI fabric design. And the third feature is that in today's AI fabrics, it carries lots of heterogeneous traffic with different objectives. Actually, many industry companies are trying to design converged network fabric to carry both AI workload and general purpose traffic. When this traffic is mixed, okay, so if one type of traffic causes congestion, it may affect the performance of another. And even within AI traffic itself, within AI traffic, we have lots of different data transmission. Okay, for example, KV transfer, activation, data transfer, outlaw, data transfer, etc. So this traffic can compete with network resource, okay, and cause contention. So that's why we need to provide better resource reservation, flow isolation between different types of traffic to provide a better QoS. So based on the previous insights, here we summarize some of our recent work in AI cluster networking. So we mainly focus on 3 directions. The first direction is traffic prediction and traffic engineering. The second direction is buffer management, okay, mainly for isolation. We design something, for better flow isolation. And the third direction is scheduling. Okay, we have designed several, large volume and high throughput packet scheduler. And also we enable this hierarchical packet scheduling in some of our recent work. Now, due to the time limit, I will only focus on the middle part, the buffer management part. We will talk about the 2 of our schemes. Both of these schemes can provide, good flow isolation with a sophisticated buffer management scheme. Now, the first one I'm going to talk about is the infinite flow. So the main idea is trying to provide a large number of VC with very limited buffer requirement. Okay, and also at the same time we want to support the lossless data transmission. So we know that the virtual channel, okay, VC has been used in lossless network to provide the hop by hop flow control. Okay, for example, in Ethernet we use PFC, and in InfiniBand, we use CPFC, credit-based flow control. So in commodity switches, this flow control has been operated on each VC individually. So for example, on this slide, we show an example of a link with 4 VCs. Okay, so each VC has a dedicated VC buffer in the downstream switch. So many research, many prior studies has already shown that with more VC, we can provide a better performance. We can provide better isolation between flows. Okay, so which can mitigate the header blind blocking, prevent PFC, CPFC deadlock. So why could we support a large number of VC? Because more VC is better, right? Why could we support a large number of VC? Ideally, we want to provide a dedicated VC for each flow, for each data flow. So that way we can eliminate flow interference. Okay, we can eliminate the header blind blocking, etc. So what's the barrier to support a large number of VC? So the problem is due to the poor buffer management scheme adopted in this VC management. So we know that in order to prevent the packet loss, each VC has to be assigned a buffer in the downstream buffer. Okay, so suppose we want to send at the rate of R, so the downstream buffer reserved for this flow should be large enough to satisfy this inequality. So if the sending rate we want is higher than the linear capacity, so the buffer size reserved for that VC have to be at least 1/2 of BDP, 1/2 bandwidth delay product. Now, if we want to support n flow, n VCs, so this number will be multiplied by n. So that's actually a cost, a linear cost. Okay, so when the VC number is too big, we cannot afford this buffer requirement. So here we show an example of the inefficiency of static buffer allocation. Okay, so in this example, we have 3 VCs, and suppose the BDP, the per hop BDP between the two switch is 15 packets. So you can say it's because of the static allocation of the buffer. Here the downstream router downstream switch has a buffer size of 15 packets. So each VC will be allocated 5 packets. So as a result, even here we have only 1 VC. Okay, there's no contention. This VC can only send at the rate of 1/3 of the line rate because the buffer space allocated for this VC is only 5 packets, 1/3 of the BDP. Okay, so that's actually a problem. So you can say this 2 parts of buffer, okay, this 10 packets of buffer has been wasted, okay, because they are associated VC, they are inactive. Now, a very intuitive idea is, can we use shared buffer? Okay, we use shared buffer between VCs. Of course, we can. Okay, so if here we can allocate all the buffer to this active flow, active VC, the VC can send at the rate of line rate. Okay, can send at the line rate. Now we have another question. Okay, how to allocate buffer space between VCs? Okay, what's the buffer requirement for all the VC as a single entity? Okay, so here we use another example. Here we have 3 VCs on this link, and the downstream buffer has 15 packets size, and the per hop BDP is 15 packets as well. So if we allocate 1/3 of the downstream buffer to each of the VC, all these 3 VCs can send at 1/3 of the line rate, supposing there's no congestion in the downstream direction. Okay, so that's good. But the problem is, okay, how do we know how much bandwidth each flow needs? Okay, in that case, we fairly allocate the buffer to each of the VC. So each VC get 1/3 of the bandwidth. But what if some VC want more bandwidth? Okay, and how do we know how much bandwidth each VC requires? So that's actually a question. But no matter how much bandwidth each VC gonna send, okay, the aggregated bandwidth these 3 VC can send is bounded by the linear capacity, okay, by this line rate. So that in other words, the downstream buffer requirement is bounded. Okay, no matter how many VCs you want to support. Okay, 10 VCs, 100 VCs. Now, actually, regardless of the VC number, the downstream buffer requirement is constant. Okay, in that case. So here the problem becomes how to allocate buffer space among VCs to satisfy, diverse requirement of the data transformation. So here comes with our goal. Okay, so we have 3 goals in the design. The first one is lossless. We have to guarantee no packet will be lost due to overflow of the buffer. And also we want to maximize link utilization. Okay. And thirdly, we want to support as more VC as possible with very limited downstream buffer capacity. So now let's first talk about which entity should be responsible for the buffer allocation. In traditional design, okay, each router, each switch has a local buffer manager. Okay, the local manager will allocate the buffer space between flows, between VCs. Okay, so that's a traditional way of doing this. Now, when the local buffer allocates space for each VC, then we need to notify the upstream switch, okay, about this buffer allocation. So the upstream can limit the in-flight packets for each VC to avoid the packet overflow, to avoid packet loss. Okay, so that's a traditional way. But this way of buffer management is very inefficient. Okay, we cannot allocate buffer precisely and timely, okay, based on the different requirements of the flow. So here, our solution is let the upstream router, upstream switch, allocate the buffer space for the downstream switch. So allocate the buffer from the upstream, okay, for the downstream UABD. So here in the upstream switch, we have a credit pool. It's shared credit pool, and when there's a backlog that we see in the upstream switch, we can use a scheduler to schedule packets, okay, and allocate the credits among these active flows dynamically. Okay, because we know that the total buffer size in the downstream switch. So with this credit pool, we can prevent any possible packet loss due to the buffer overflow. Okay. So with this UABD, we can enable immediate buffer allocation for downstream buffer, regardless of the traffic arrival pattern. So here, let's use the example to show how this works. Okay, so in this case, the per hop BDP is 16 packets, and assuming that the downstream buffer size is also 16 packets. Now in the upstream switch, we have a credit pool of 16 packets as well. Now we have 2 VC, okay, competing for the link. So suppose here the scheduler is a round-robin scheduler. So you can see, suppose we serve this yellow flow first, and then followed by blue flow. So each time when we serve a packet, a credit will be consumed from the credit pool. Okay, and the downstream space will be reserved for this packet, but it's a virtual reservation. Okay, so you can see, when time flies, more and more space has been reserved for these in-flight packets to prevent loss. And here in this case, there's no congestion in the downstream direction. Okay, no backlog, no back pressure. So that's why packet can depart from the downstream switch immediately. So you can say, although there are lots of space reserved for this in-flight packets, there's no standing queue in this example. Okay. Now all the credits have been allocated. Okay, so all the downstream space has been reserved and allocated for these 2 flows. Okay, so in this case, you can say because we are using round-robin scheduler, so each VC will get 50% of the line rate. Okay, does this resolve all the problem? The answer is no. What if one of the downstream direction got congested? Okay, maybe due to the slow processing of the destination host. So you can see some problem gonna happen. So let's assume the blue flow or the yellow flow encountered a downstream congestion, and the downstream output rate becomes only 1/4 of the line rate. Now, because here in the upstream switch, we are still using round robin scheduler. So you can say the incoming rate to the downstream buffer of the yellow flow is 50% of the line rate, and the egress rate from the buffer is 1/4 of the line rate. So the yellow flow start to build up, okay, and occupy, queuing space in the downstream buffer. So at the same time, you can see the available buffer space can be allocated to the blue flow is also reduced. And the blue flow's transmission rate also reduced to 1/4, okay, due to the congestion encountered by the yellow one. So this basically means the congestion can propagate between the flows due to the buffer sharing, okay? So basically in this example, okay, the congestion propagation is due to the shared buffer. So that's why we need to limit the credit allocated to a VC if the VC has a backlogged queue. Okay, we want to eliminate backlogged queue. So here we designed a buffer usage control protocol, BUCP, between neighboring switches. And each VC will be given 3 states, okay, in-flight packets, threshold, and backlog. So the downstream switch will report the backlog information of each VC using these feedback packets between the two switches. So if a VC, okay, is noticed the large backlog in the downstream switch, it means that it's overcrowded. So it should we should reduce the threshold. Okay. Otherwise, if the downstream backlog is too small or nearly 0, that means it may be under credit. We can allocate more credit to that VC to increase the sending rate. So with this dynamic threshold adjustment, we can reduce the backlog of the queue. But we don't want to reduce the backlog of the queue to 0. We want to maintain the backlog queue at a very reasonable range to prevent the bandwidth waste. So finally, due to time limit, we will skip lots of details. So here we have 4 features which can be achieved by infinite flow. One is lossless transformation. Second one is weighted coupling, buffer requirement from the number of VC. So we can support almost arbitrary number of VC with a single per hop BDP buffer. And also, in this design, we integrate buffer allocation with scheduler. Okay. So in our previous example, the scheduler is round robin, but we can of course use other schedulers such as weighted round robin, strict priority, etc. Now, and also in our design, we have a feature 4. We can achieve very good rate allocation and rate control without end-to-end congestion control. Okay. As long as we have enough VC for flows. So here we have a small animation. Let me see if I can play.
This video visualizes an NS3 simulation of infinite flow, where the hosts do not implement any end-to-end congestion control or rate adaptation mechanisms. First, let us start a red flow. Here we go. When the red flow runs alone, there is no backlog. Then let us start a blue flow. When the 2 flows coexist, transient backlog builds up in the buffer. Through back pressure, infinite flow can quickly reduce the backlog. In the steady state, the 2 flows evenly share the bandwidth, and the backlog remains stable at several packets. Next, let us simultaneously start 3 yellow flows. At the beginning, the queue grows rapidly, but don't worry, infinite flow can handle it. Since this experiment adopts a round-robin scheduling policy, the aggregate rate of the 3 yellow flows reaches 75 gigabits per second, while the blue flow is limited to 25 gigabits per second. Meanwhile, under InfiniFlow, the red flow fully utilizes the available bandwidth on the bottleneck link, achieving a rate of 75 gigabits per second and satisfying maximum fairness. Now, the yellow flows are about to complete their transmissions. We will see that after the yellow flows depart, the small standing queue of the blue flow can effectively reduce the bubbles during this transition process. As we can see, the transmission of the blue flow is almost uninterrupted during this transition. Finally, let us finish the residual stage of the experiment. This video visualized.
Okay, now let's talk about the evaluation. So we look at this infinite flow on a Xilinx U280 FPGA board, and the left figure shows the buffer size requirement. As you can see, no matter how many VC we want to support, infinite flow only require a constant buffer space. Okay, 64 kilobyte, even under 16,000 VC. And this result didn't consider the pervasive state overhead. So if we consider pervasive metadata state overhead, that's on the right figure. So when the VC number was small, majority of the cost is from the buffer, packet buffer. So the VC metadata cost can be ignored. When the VC number increase, VC state overhead will become dominant. Okay, but this number, although it's increased linearly, but the slope is very small. So even under 16,000 VCs, each port only require 400 kilobytes of data. Now, suppose we want to implement a switch with 64 ports, the total memory requirement is only 25 megabytes. So it's very acceptable. Okay. And also we have done a large scale S3 simulation and different workload. As we can see, we compare the infinite flow with CPFC, PFC alone, and also we compare with PFC combined with DCQCN, end-to-end congestion. Infinite flow always performs the best. And please note that this performance is achieved without using any end-to-end congestion control. So basically that actually answers one of our previous hypotheses. With enough VC, in ideal case, one VC for each flow, we don't need end-to-end congestion at all. Okay. Okay, so because of time limit, I will skip the second part of the talk. So now let's use this slide to conclude my presentation. So as we know that in AI era, the AI traffic is very, very different from traditional conventional data center applications. We have a more periodic, synchronized burst traffic, and lots of different types of periodic traffic mingled together and competing for the network resource. So that's why the network design have to shift from traditional general purpose packet forwarding toward a more intelligent, workload-aware infrastructure optimized for AI computation. Okay, so that's all for my today's talk. Thank you.
Okay. So time for one question. Thanks. Very good thought. But the one thing I'm wondering is that so when you define the number of VCs in a network, actually it's a little okay. So the thing is that for many this number of VC, many that you a application flow do this, you have a
some instances.
Actually, in our design, there is no entity, no single entity to manage the assignment of the VC. We can assign VC basic, for example, using, dynamic, maybe first come, first assign manner. So whenever you have a new flow comes, we can build the flow, UVC, okay? We can do a maybe quick hash using the packet header.
The back can be done in the end. Every stage.
And switch now.
Yeah, so you need to go through the first.
Yes.
Okay. So then for short flows is kind of look at that.
Yes, yes.
Okay, so Professor Xu has, I think you have three here, right?
Yeah.
Here. A related topic, so you can have the game offline later. Okay, let's start the speak again.